Okay, so we're in the whole chapter. We're looking at what happens when you change the magnetic field. And this problem keeps coming up about, it's called motional EMF. I put emotional just to be funny. You know, I can be funny, right? Okay, so I'm going to go ahead and tell you the answer, and then I'm going to show you two ways you can get this expression. So if I take a metal bar, there's my metal bar, and I move it in a magnetic field at a constant velocity, a constant magnetic field, so the magnetic field's going into the paper, and the bar has the length L, then this will generate a change in electric potential across that bar with the voltage of B times L times V, where V is the velocity of the bar, L is the length of the bar, and B is the magnitude of the magnetic field. Okay, so like I said, let's do this two ways. So let's first consider this bar. And I'm going to redraw it because I redraw things. I have no idea why. And let's consider a positive charge in there. And it could be a negative charge. It doesn't really matter. I'll show you the difference between those in another video. Now, I have in here, this charge is moving. It's in the metal, so it's moving that way with the velocity v. And the magnetic field B is into the paper. So there's going to be a magnetic force on that charge. So I've brought out my little Lego QV cross B. Remember that the force F is perpendicular to both B and QV, and we use the right-hand rule to do that. So you could do it this way. You could put the QV in the direction of your finger, B in the direction of your middle finger, and your thumb would point in that direction. Or you could use your little tool here, and it looks like that. So there's going to be a force pushing this up, magnetic force, FB. So after some time, we're going to get, I draw my thing really big, positive charges up here because they get pushed up to the top. And, well, the whole bar is neutral, so we're going to get negative charges down here. The bar is still neutral, though. These charge difference is going to make an electric field inside of here going this way. And this electric field is going to also exert a force on there. And so what's going to happen is charges will continue to build up until Fe, the electric force, is equal to, that was weird. Fe, the electric force, is equal to Fb, the magnetic force. So the electric force is going to be equal to Q times E. That's the magnitude, right? I've already got the direction set. And that's going to be equal to the magnetic force, which is QVB. Remember that FB equals QV cross B, but we already have the direction, and they're perpendicular to each other, so there's no sign value there. And then Fe, the electric force, is just Q times E. Okay, so the Q's cancel. And then I have the electric field is VB. Now, what if I want to go from right here to right there and find the change in potential? And if the electric field's constant, delta V is going to be negative E delta S, if you want to think of it that way. But I don't really care about the sign. I care about the value. And delta S is going to be L. So I get EMF equals EL, but E is VB. So I get BVL. That's it. Okay, let's do it again one other way. I'm going to put this one in a slightly different situation to make it look a little bit better. So suppose I have a wire like this. And I have a bar that I can move. Now if and then I have a constant magnetic field B going into the paper, same thing. It's the same bar. It's still length L. I'm still moving with a velocity V. Now, what makes this different, a little bit different, is if I can move this bar, it's going to generate a change in potential, and there could be an electric current too. Okay, but that's not really super important. It's just easier to picture in this case. So let's use Faraday's law. So Faraday's law says that the EMF is equal to N delta phi B over delta T, where the magnetic flux is equal to B A cosine theta. And theta is the angle between B and the area. So in this case, I'm dealing with this is my area. And so the area would be in the same direction as the magnetic field. So this is just one. It would be BA. Okay, but I need to find the change in flux. So let's imagine some short time interval, and this bar has moved over here. It moved a distance delta S. I know that if it's moving at a constant velocity, v is delta s over delta t, so delta s is going to be v delta t. So now I need to find the change in flux. EMF is going to be flux 2 minus flux 1 over delta t. So this is flux 2. Let me draw it like this. It's this area, and flux 1 is that area. So this is flux 1, and this is flux 2. So let's just write that out. EMF. This is called this an area A. I don't know what it is. I don't really care. Okay. So flux 2 is going to be this area times the magnetic field. Okay. So that's going to be equal to B times A. That's this. But I also have this area. This area is going to be of length delta S times L plus delta S times L. Because that's the size of that rectangle right there. And then I have to subtract off the initial area, which is just going to be the initial flux, which is going to be B times A. And all of that divided by delta T. So now I get B times A minus B times A, and they cancel. So I just get B delta S L over delta T. And oh, look at that. Delta S over delta T is B V L. Boom, did it. The end. All right, physics people, another video later.